A tensile test is a great way to see how strong a material is. Let's take a look at what a tensile test will tell us. A tensile test is a way to see how strong a material is by pulling on it. To perform a tensile test, we first need a sample of the material we're interested in testing. These samples are called test specimens, and they usually look like little barbells. These specimens are often called dog bones because they're wider at the ends. This helps the specimen break in a predictable and repeatable way. The test pieces can be round or square or even tubular or other shapes. Next, we need a machine that is strong enough to pull the tensile test specimen apart. We'll use this old government surplus tester today. As this machine pulls the specimen, it tells us how much force it's pulling with. When I turn the crank on this tensile tester, it turns a gear that slowly moves the grips apart. It's hard to see, so I'll set this indicator on it to show you. Now you can see that the grips slowly move away from each other as I turn the crank. When we do a tensile test, we want to see how much stress builds up in our sample. Remember that stress is a force divided by a cross-sectional area. The gauge on our tester gives us values of force in pounds. To get stress values, we'll divide the pounds by the cross-sectional area of the sample. The sample we're going to test is 0.450 inches wide by 0.134 inches thick. So the cross-sectional area is 0.0603 square inches. We'll want to know about strain too. This device, called an extensometer, will measure how much the specimen is stretched. We'll set it so that these knife-edge prongs are 2 inches apart. We'll call this the gauge length, and this will be our original length. Then we'll measure the amount the dial moves and divide by our 2-inch gauge length. Remember that strain is the change in length divided by the original length. Now, as I begin turning the crank, you can see that the value on the force gauge dial quickly rises, while the dial on the extensometer barely moves. But as I keep cranking, the force gauge dial almost stops increasing, and the extensometer dial starts moving more and more. Eventually, the dial on the force gauge drops down a little bit. This red drag pointer shows where the force reached its maximum. This drop tells me the sample is about to break, so I'll remove the extensometer so it won't get damaged. As I keep cranking, I can see the sample start to neck down, and it breaks. Let's plot this on a diagram. We'll put strain along this axis, and we'll label it with a lowercase epsilon, or a Greek letter E. We'll put stress on this axis, and we'll label it with a lowercase sigma, or a Greek letter S. Now let's take some values from our test to see the relationship between stress and strain. When we first began turning the crank to pull the sample apart, the stress built up quickly, and there was very little strain. Notice that the graph for this region makes a straight line. But as we kept cranking, the part started stretching, but the stress only increased by a small amount. Eventually, the stress started dropping, and a small neck became visible on the part. We removed the extensometer and kept cranking. The part necked down even more and suddenly broke. That was the end of our test. This necking behavior happens in ductile materials. Here's a video of a brass part necking down. Here the necking is really easy to see. If a material doesn't neck down like this in a tensile test, we know that it won't bend very much without breaking. Now let's take a closer look at that diagram. You can clearly see two different behaviors here. At first, the relationship between stress and strain is proportional, or linear. Do you remember elastic deformation? Well, that's what's happening here. The atoms of metal are just being stretched apart, but their structure is not changed. But eventually, this will reach a limit, and the atoms will be moved out of their position in the lattice. This is called the yield point. Beyond the yield point, the metal stretches without generating much more stress. It begins to elongate and is permanently deformed. The type of deformation happening here, you may remember, is called plastic deformation. During plastic deformation, the rows of atoms slide past each other and will never go back to the way they were before. Eventually, the material flowed so much that this neck formed. As the neck formed on the sample, the stress on our part started falling back down again. Eventually, the specimen broke, and that was the end of our test. We can learn a lot about a material by performing a tensile test and generating its stress-strain diagram. With this diagram, we can start talking about strengths of materials in a much more meaningful way. We can also see how easy or hard it would be to shape a metal, and we can see the different ways that a material could be useful or some of the limitations it might have.